I move on to the next talk. The next talk is by Yoshua Bengio. He's one of the biggest shot in our community, Turing Award winner. But from my perspective, one of the sharpest brains I ever encountered. He's a very good guy. And now he's on our side to fight against the coronavirus. Yoshua, it's your stage.
Thank you, Sepp, for these kind words. Let me try to share my screen. Wait, what is it? I don't understand what it's asking me.
It asks for permission.
Desktop 1, is that what I want?
Oh.
Yes. Shit. Sorry, you guys. It's asking me to open my preferences. I thought this was already done.
Yeah, you have to allow the capture of your screen.
Yes.
You have to log out and come in.
So you will have to go out and come in again. So maybe as a step, you might want to take one question in the meantime.
That's a good idea.
We see already the slides.
Oh yeah, right.
Oh, okay. So let me start quickly. So I wanted to go over a few things that are going on at MILA. Actually, I'm going to talk mostly about two projects, and one is about drug discovery, but the other is more about contact tracing. Let me try to do a screen share. Do you see this? Do you see the screen properly?
Yeah, we see it. Yeah.
Okay. So I mean, I want to start by saying that I'm quite enthusiastic about the solidarity that I'm seeing in the scientific community in general and in the machine learning community in particular. People are stopping what they usually do and forgetting about publications and egos and money and all the competition we usually have, and just focusing on saving lives. So at MILA, which has about 400 researchers, mostly grad students doing machine learning, many projects have started. There is also an effort to coordinate the different projects within Canada, organized by CFAR. This is a website for this. I guess the slides will be available later or something. Yep. So at MILA, we also have a webpage to list different projects. One of my postdocs contributed to a paper that's now an archive to try to survey the different machine learning methods that were published to try to fight COVID. And that was already like last week, but things are moving very fast. So covering things like diagnosis, drug discovery, AP models, social media. So I'm going to just talk about these two projects that we're working on, contact tracing and drug discovery. Sorry. Okay, so I want to mention a paper that just came out yesterday. Things are moving so fast, it's amazing. In Science, where they used a form of epidemiological modeling in order to demonstrate in simulation that if we can do digital tracing, contact tracing using phones, rather than what is commonly used in many countries, including what is going on currently in Canada, that is, hand tracing by, interviewing people and asking them who they met. You can actually have a very significant impact on the R0 of the disease, bringing it below 1. So I think this is a very important ingredient in the fight against COVID-19. So we are developing such an app. It's not just people at MILA. We're collaborating with people from around the world, people also in companies. And we're starting from the code base of MIT Media Lab that has an app called Safe Paths, where there are hundreds of developers that are contributing, and we are also adding our own contributions to this. The two particular things of the way that we're developing our app is on privacy and machine learning. So on the privacy side, I will explain that there are challenges because it's kind of it may seem like a contradiction to have both privacy and being able to protect I mean, to intersect people's trajectories and to protect privacy, and yeah, together. But it's really important for us in Canada because both the government and the public would not accept an app which doesn't match our sort of cultural expectations. And if we don't get a wide adoption, then the thing is not very useful. And I don't think the government will force people to use something like this. So it has to be something that people accept. On the machine learning side, the advantage of using machine learning is that in addition to just telling a person or their app that they were in contact, say 5 days ago with somebody who later tested positive, now you can combine a lot of pieces of more fuzzy information, like I've met a bunch of people, we don't know what their status is, or maybe I met somebody who met somebody who met somebody who was tested positive. What does that mean for my own risk? So that's where you need machine learning, right? But before I go there, let me go through a little bit of the privacy versus health. So from a ethical point of view, we really have two conflicting values that somehow we need to try to find a good compromise over. And I think that's where technology can be used. But there's still going to be a dilemma, and maybe the solution is going to be different in different countries, depending on how much you value privacy, for example. So for example, should governments have access to your full trajectory? In many countries, people would say no. We don't want people to know where you've been. We don't want people, we don't want a government or say the police to know who you've been meeting. Another ethical concern, which is important, is, and not maybe less obvious at first sight, is that if the information about who is high risk or infected becomes public information, or somebody that some information you could get if you're close to a person and somehow their phone tells your phone that they are a high risk, so that you can stay away. It might seem like a good thing, but then you might turn against that person and stigmatize them. And this question of human dignity here and human rights, which have to be balanced with the advantage of having information that helps people avoid risks, or even that deter people from acting irresponsibly. So think about if you knew that when you walk around the city, that others that cross path with you might know your risk level, and if you have a high risk, even if you're irresponsible but you don't want other people to reject you, you might decide that you stay at home and do what the government told you to do. But on the other hand, that goes against the privacy requirement that we don't want the infection status, infection risk of a person to be revealed to others. So we have these contradictions, and we have to understand them and then use technology to our best to try to find a good compromise. Now, one thing we are trying to do here in terms of strategy is start by deploying an app which will be very strong on privacy, and see how far we get in terms of reducing the R0, the rate of spread of the virus, because there's a threshold value of 1, as many of you know. And so if we can combine with many other things that are going on in society, if we can get the R0 below 1, then you're basically done. And then we don't need to endanger democracy and privacy. And of course, if it doesn't work, then governments probably want to push more on the pedal of less privacy and stronger health protection. Okay, so one of the key ingredients that we're working on to try to find a good compromise is a set of algorithms that do what's called private set intersection. So what this is about is I have a set of points where I've been at time, location points, and you have a set of points, and would like to find the intersection of those points, but we don't want to have have access to each other's sets, right? So it sounds like it's impossible, but people in cryptography and so on have been working on these things, And there are solutions that are not necessarily perfect against all attacks, but they're pretty strong. And it turns out that we've been working with this group that just pushed out a paper maybe a couple of weeks before COVID became a big thing here. And you can find their paper online. It's called Contact Tracing Mobile Apps for COVID-19, Privacy Considerations and Related Trade-offs. So what's important in this method is that the trajectories stay on each person's phone, right? That's so we can have a sort of peer-to-peer exchange of information using the private set intersection algorithms. The ideal scenario is if we can get Bluetooth to work, but there are Bluetooth implementation issues. If you have Bluetooth, then you can guarantee that it's only the phones that were physically close to each other that are going to exchange this random key that could be generated when they're close to each other, that is going to later allow them to exchange information. So you need something like this, right? That we have a way to communicate after we've met, so that if I get infected and I know about it, I can tell you that information in an anonymous way. The general idea is we're going to convert this this random key into a private mailbox sitting in a server, and only people who have this private key can either read or write from that mailbox. In addition, the way that that information is about, say, my location and so on is going to be converted into a mailbox ID can be split across multiple servers. And the idea of this is that even if some of the servers are compromised by some attacker, they would not be able to unlock those mailboxes. They would have to be all like colluding in order to have access to that information. Okay, so that's the privacy consideration that we are working on and implementing right now. The machine learning considerations. So what are we trying to do, first of all? So what you want is that each phone tries to predict the posterior probability that the person was infected for each of the days, say, in the last 2 weeks. 2 weeks because this is a time when you could have been infecting somebody. And you want that information because it's not my status now that matters for the person I met 6 days ago. It's the probability that I was infected 6 days ago. And so you want to keep that. You want to compute those posterior probabilities for all the past days. Say, I mean, you could do hours, but days is probably fine. So we can't afford to compute the joint probability of everybody's infection status. And I mean, that would, anyway, it's hard to represent that anyways. And because we are doing this peer-to-peer thing, we can only compute things locally. So we're going to have the different phones communicate with each other about their beliefs that they're being infected. But there's a chicken and egg problem, because my belief becomes an input. My belief that I was infected, say, 6 days ago, becomes an input for your calculation of your belief that you're infected now because you met me 6 days ago. And so we depend on each other's beliefs. Okay. And then the right way to think about this in machine learning is to think of the different phones exchanging information so that they can converge to a consistent estimation of the marginal distributions over all the phones of all these probabilities. And loopy belief propagation seems the right kind of algorithm to achieve this. So we are implementing these things. Now, within loopy belief propagation, you still need to estimate these conditional probabilities. And that's where we might use machine learning, or even simpler models, which we want to put on the phones before we get data, that are based on epidemiological model, epi data that are currently being collected from around the world. So these models would be very simple. They might be like naive Bayes models. But what's nice is we can put them on the phones right now. We can also use those models, and we have done that, so to build simulators. So the same way that epidemiologists are building simulators, So these models can then be used to generate training data for machine learning models. That training data could be used to pre-train our predictors before we get enough data from the real data collection of the app, which is going to take at least a week, maybe 2 weeks to get enough data because of the delay between things happening and test results. So these simulation models are very important. Other considerations is the information exchange. Unfortunately, in order to preserve privacy, the messages that are being exchanged between phones have to be quantized. Otherwise, if I sent a very, very precise real value, and then the other person colluding with someone else could potentially figure out that was coming from me, because it would be like a unique key that identifies me. Whereas otherwise, the only information a phone would have is, 6 days ago, I met this person for 15 minutes, and their risk level was 0.7. I mean, level 7, on 1 to 10, and that kind of quantization makes it impossible to trace back the information to me. Sorry, I didn't keep track of time. How much time do I have left?
Only a few minutes. You have to speed up. Okay,
sorry. So now I'm going to just quickly say a few words about this. This is my last slide about drug discovery projects. Just to give you a gist of what we're doing. So we're building neural nets that can predict the binding energy of candidate drugs or pairs of drugs with target proteins that the virus needs to be active. We are pre-training those neural nets by generating data from a physical docking engine that we have optimized to be very, very fast. So right now we can generate, for example, 200 million examples, which associate a particular molecule that's, say, initially randomly picked with the thing we want to predict. How well does the molecule bind to the target protein? Now, these are not the real binding energies, but they're pretty good estimators that can be used to pre-train networks. And then the molecules that look good then will be subjected to biological assays. There's also assays that are coming on currently. So in particular, Bill Gates paid Scripps to screen 20,000 existing molecules. We're working on screening pairs of molecules. So it's never going to be able, we're never going to be able to screen the 400 million possible pairs. So we have to use virtual screening to select out of the 400 million possible pairs of drugs, those that may be promising before they can be tested with biology. On the front of synthesizing new molecules, we're using an RL framework which we have been working on for a few months. That's an extension of AlphaZero, so it uses multicolor tree search, and it uses a representation of molecules based on rigid fragments. You can think of just the building blocks that form these drugs. And that makes the RL work really a lot better because you have sort of more abstract actions, and it also makes those molecules more synthesizable. And finally, one of the challenges in this thing is the true reward function would be like the biological assay, but that's too expensive. And so, and a slightly better reward function is calling the physical docking, but that's also very expensive, but not as much. It might be taking minutes to do that. So then we're going to train these neural nets that estimate what the docking would do. And then during the reinforcement learning, we want to have actions that say, I want to call this oracle. I'm going to pay a big price now to have an actual docking simulation rather than use the neural net, or even a bigger price to actually ask our friends that are working nearby to test that molecule for real in biology. So all kinds of interesting machine learning questions are raised, and this is just starting for COVID, but we have been working on this for other viruses before, so we are in a good shape. Thanks.